Thank you very much. Thank you very much for give me an opportunity to give a talk in this interesting conference. I would like to talk about the relation of the double Hill theory and supergeometry. Some people, some speakers already talk about double Hill theory and supergeometry. So I briefly summarize our purpose, and we want to understand the geometric structure of T-duality and the double Hill theory, DFT. Supergeometry is a very clear, it proposed very clear method to understand DFT, geometric structure of DFT. There is some complicated structure, section condition generate Bianchi identity, and so on. So, and another method is to we would like to simple method to compute complicated equations and so on. Okay, so in order to analyze this method, we use supergeometry. Okay. From talk is as follow. First, we briefly summarize double history and supergeometry, and we go to the application of this method to supergeometry and other physical situations. Okay. First, double Hill theory. DFT is the manifest T-duality invariant formulation of the supergravity, and we combine original manifold M and T-dualized manifold M tilde to two-dimensional, 2D dimensional double space. But in this talk, I don't concentrate the product space. We only consider 2D dimensional double space, M hat. First, we mentioned our notation. Hat indices show the 2D dimensional indices. Unhat indices shows the D-dimensional indices like this. And Mn like this, and so on is space-time indices, and AB is a target space flat indices. Double Hill theory has we assume a double Hill theory DFT assume ODD invariant metric, ODD invariance. So we assume invariant tensor, this metric, and this assumption is the so-called generalized Lie derivative. This is generalized Lie derivative is defined like this. But problem is this generalized Lie derivative is not closed. The delta M is not 0. This means this condition is not satisfied. So we need some consistency condition. This is the so-called strong section condition or strong section condition. This is this condition. If this condition is satisfied, this equality is satisfied. So by this condition, we choose a physical D-dimensional subspace. This where the phi beside any field and gauge parameters. Okay. So we introduce generalized metric HMN. This is typical parameterization is like this. And G and P and metric and normal B field. But we consider field by formalism. So we choose field line, generalized field line. Typical parameterization like this. This is a small e. It shows the normal field line in supergravity. So in order to introduce field line, we need flat metric, ODD flat metric, and double local Lorentz metric, SAB. And relation of each metric is like this. This is the relation. This is the relation of the curved metric and flat metric. This is the relation of the field line and the generalized metric. So field line satisfies this generalized Lie derivatives equation, so we can obtain the generalized Lie derivative of the generalized metric from this equation. Okay. Okay, we go to supergeometry. In some sense, this is the precise definition of the graded manifold. We consider generalization of manifold. It is each coordinate has a z-graded degree grading. This is a precise definition, but anyway, we consider z-graded even and odd coordinate manifold, and we connect properly. We connect each coordinate properly by coordinate transformation. The grading is called degree. We denote it as function of like this. And we consider only non-negative degree graded manifold. So this manifold is called N manifold. There are several naming of this structure. We consider structure on graded manifold. We call QP manifold, pre-QP manifold. Pre-QP manifold is the N manifold with two structure. First structure is omega. It's a graded simplex form of degree n. The graded we can obtain graded Poisson bracket of degree minus n from this simplex structure. And next one is the graded vector field of degree +1, which we require a compatibility condition of two structure. This one. And normally we can obtain the Hamiltonian function of this vector field, graded vector field like this. We assume that this Hamiltonian function, if this is our structure, if Q square equal to 0, it's in this case this is called QP manifold. This Q square equal to 0 is equivalent to this equation of Hamiltonian. This is called classical master equation. This theta is correspond to a kind of BRT charge. This BRT charge of the so-called AKST sigma model. So we can obtain a kind topological sigma model from this BRT charge. Okay, we consider. I explain a technique, our technique, by the typical example. It is the simplest, most famous case. This is a Courant algebra case. Okay, this is a so-called derived bracket construction of Courant algebra. Okay, we consider some double cotangent boundary. This 2 and 1 is shows the degree of the cotangent coordinate. In the local coordinate, locally we choose the x pair, this coordinate. This coordinate is this coordinate on this space of degree 0 and 1. G and Qi is a canonical conjugate coordinate of degree 2, 1. So naturally, we can define this simple structure, and we can define Poisson bracket. From degree counting, the Hamiltonian function must be of degree 3. So simplest one, we can choose this Hamiltonian function. So this Hamiltonian automatically satisfies the classical master equation, and Courant algebra is constructed as follows. First, we choose degree 1 function. Degree of function is this one. This corresponds to the sum of vector field and one form, as like this. So this function is considered the section of Tm plus Tm. So this is the correspondence of coordinate and basis. We consider so-called derived bracket. Derived bracket is this double bracket. So we compute the derived bracket of this degree 1 function. This gives the so-called Dorfman bracket of Courant algebra. This is a beautiful equation, and derived bracket with the function give the so-called anchor map of Courant algebra, and the identity of the Courant algebra is given by the classical master equation. This one we can prove, and all the identity from this one equation. Okay. So we apply this derived bracket construction to DFT case okay. We consider 2D dimensional double space and the same cotangent bundle and the similar symmetric form. So, and we consider degree 1 vector field. The generalized derivative, we define generalized derivative by a derived bracket like this. This is a reasonable definition. This is v and v prime is a function of degree 1. Okay. Later we showed. I show this is in fact the generalized Lie derivative in DFT. Okay. This we consider section condition, so-called closure condition. We call closure condition. In this, we don't require this classical master equation in our case, in generalized Lie derivative case. But so this Jacobi type identity is broken by this term. This is automatically we can compute the Poisson bracket of this one and using Jacobi identity. So, but okay. So if this term vanishes, we can obtain the Jacobi type identity. So the generalized Lie derivative is consistent. Cyclic sum is this term, only one term appeared, and that's the breaking term. Right, yeah, right. Okay, it is we have two cases. case one is that the classical master equation is satisfied. If this classical master equation is satisfied, this equation, this term vanishes, so we obtain this equation. So this is the Dorfman bracket case of Courant case. So this is okay. Another case is this classical master equation is broken, but if we take Poisson bracket FGH, if we take this equation is 0, in this case, a DFT case, we restrict function to the space, and the space to satisfy only the function satisfy this equation. This is nothing but section condition, right? Geometrically we consider only some special section. It's it's similar to the Dirac structure. We restrict to the section. We consider only some section in the total space. It's similar to Dirac structure, but it is not not precisely the same mathematically. This is the new geometric relation, I think.
Right, but the Dirac structure is similarly different somehow. So here there should be also some problem.
But so this is not the Dirac structure. Okay, so okay.
What happens is that you can construct a polarized structure and you polarize it's like a certain stuff.
So you satisfy this master equation and some
Right.
You take the double space, but then you say, okay, I want to polarize structure, and you don't do that anymore, but as long as all variants of this
Okay. Okay. I demonstrate. This is in fact this equation. In fact, the section condition in DFT. So we choose this product manifold, and we choose I choose the local coordinate expression of this one. This is the super coordinate of degree 0, 1, 1, 2, and we consider this simplex structure. In order to obtain the precise DFT cases, we should change basis like this. We should change basis to P prime, Q prime basis from this one, like this. This is only the technical reason. If we change this basis to like this, we obtain this Poisson bracket relation. And the correspondence to the normal coordinate is like this. So we choose the most simplest theta. It is this one, and we compute the derived bracket. So we obtain the correct generate derivative of vector field, or generalize vector field. Okay. This theta do not satisfy classical master equation like this. So we compute this closure condition in supergeometry. So we obtain this equation for if this equation is for the case of the FGH, all FGH are the vector field. So this equation is equivalent to this section condition. And for function cases, this is similar. We obtain similar equation. So anyway, this equation is equivalent to this section condition. But this is V1, V2, V1, V2, V3 is the FGH. V1, V2, V3. Oh, sorry. But we can rewrite this section condition to coordinate independent equation. Okay. Okay. Next, we want to consider fluxes and this Bianchi identity. In order to introduce flux, we have one technique, twist. Okay, twist is this equation. This for function f, twist by alpha is defined by this equation. Exponential adjoint action by alpha, but where alpha must be degree 2. This is important. If alpha is degree 2, degree is preserved by twisting, and we obtain this a kind of canonical transformation relation. So, precisely speaking, alpha is a local function. It's a kind of jar, a stack of groupoid. Okay. So I comment about the relation of twist and section condition. By twisting, Hamiltonian function changes like this. So the closure condition changes, but we consider we properly choose alpha so as to d-dimensional physical subspace does not change. By twisting, the d-dimensional physical subspace does not change, but for the section condition for the vector field changes. We need a kind of connection. Connection is introduced in the section condition, right? Later, this introduction of connection is important. Okay. In order to consider field by formality, we introduce local Lorentz frame super coordinate, and we consider DFT basis. Okay. If in this case the possible twist is only three twists. This twist is the binary function of P prime, and we have space-time frame and local Lorentz frame. So it's the local frame. This is the function on space-time function, and this is the hybrid function, right? The alpha, we have possible alpha is three types of alpha. So this is a formula. And the interesting thing is the twisting by E. This E is a hybrid one. By twisting by E, some connection is introduced. This is so-called generalized Weizenberg connection. So we have a connection term. So by E twisting, the first original simplest Hamiltonian theta zero is twisted, but we have some extra terms. This term is interpreted as the flux terms. Okay, we see this is in fact flux term. This is F and theta. We can obtain theta is expressed by like this by E and Weizenberg connection. This is nothing but the generalized flux and the generalized Weizenberg connection proposed in this paper. Okay. Okay. Now we consider Bianchi identity of these fluxes. Okay. I consider first I review Bianchi identity of flux in its supergravity cases in supergeometry. In the supergravity case, this manifold, the QP manifold, the classical master equation is satisfied. And the classical master equation after the twisting is nothing but Bianchi identity of all the fluxes. In this case, most general Hamiltonian function is like this. So this is the binary term. This is quadratic. This is the square term. But this term is interpreted as H flux, F flux, Q flux, R flux in some general fluxes. Okay, we consider simplest case is the original Nouveau-Schwarz H flux case. This is only the B. There is only B field and H flux. In this case, we consider only B, so-called B transformation, B twist. In this, okay. Yeah. Yeah, we have a simple formulation in the pre-keeping case. Yeah. So, but in this case, it is a QP case, not yet, not pre-QP case yet. QP case is B transformation give rise to this term. This is nothing but H flux. So classical master equation. From classical master equation, we obtain the normal dH equals dH is close this equation. We can consider more complicated cases. They propose this more complicated for definition of four fluxes, where the B is a B field and the beta is beta field, beta transformation, and nabla is a covariant derivative using metric and connections, and T is a torsion. So there is they propose this for fluxes we can obtain the Bianchi type identity from this the direct of these four flux by direct computation, but my claim is we can summarize the equivalent. We obtain equivalent equation, or equivalent only one equation, classical matter equation. we can consider for twisting, this is the alpha. For alpha, and we obtain this twisting, we can consider this twisting, and we obtain some complicated theta too. But if we impose this classical master equation, we obtain all the Bianchi identity of the 4 flux proposed in this paper. So my claim is that this classical master equation is equivalent to the Bianchi identity of all the fluxes. Okay, we go to the pre-QP case. We go to DFT case. DFT case, this classical master equation is not satisfied. So we need modification of this equation. Our proposal is this one. Okay, first we consider this. We obtain this Hamiltonian function with fluxes, 2 fluxes by twisting. So the Bianchi identity, a kind of Bianchi identity is this one, where the theta classical master equation is not satisfied. So this term is not 0, but if classical master equation is satisfied, this is trivially 0. So we obtained this one. We obtain only first term, and we recover classical matter equation, the Bianchi identity of the supergravity. Okay. Okay, this is okay. We confirm that this is the okay in the concrete cases. So we compute twist. So we obtain this equation, and we obtain these 5 equations. First 2 equations, the definition of the F flux and the phi fluxes. And second, third equation, the third equation is generalized Bianchi identity in DFT, proposed this paper. Okay. So we obtain the correct answer, correct equation. And the fourth equation is the new Bianchi identity for phi. So this is in fact satisfied if we we choose this proper definition of the phi and f. We found the new Bianchi identity. And the fifth equation is trivially satisfied. Okay. In the concrete case, this is this gives the correct answer. But we can generalize more. But we can more general twisting, and we can make a general twisting. And we can obtain more general Hamiltonian function like this. So we can substitute this general Hamiltonian to this Bianchi identity. So maybe we can in fact we can obtain the more general generalized Bianchi identity for the many fluxes, but we don't understand the meaning of the other extra fluxes. It is not correspond. It's not. These not correspond to the fluxes, generalized fluxes in DFT and supergravity. This is a next problem. Okay. But we obtained a simple method to obtain a generalized Bianchi identity in DFT. Okay, briefly, I briefly explain the applications of this formalism. The first one is the generalized Sharp-Schwarz twist compactification. Okay, we briefly explain general Schack-Schwarz compactification, GSS. And we consider 2D-dimensional target space and divide external space and internal space, X and Y. And generalized field buying is, we assume generalized field buying is the product of the external function and the internal function. This is the Schack-Schwarz assumption, Ansatz, Schack-Schwarz Ansatz. And similarly, gauge parameter is divided to external function and internal function. And we can obtain some generalized fluxes, like this generalized connection, generalized Guitenberg connection, that we can obtain some generalized Bianchi identity. And this is the generalized Lie derivative in the GSS compactification. Then we obtain this section condition gives rise to this external section condition and the internal Jacobi identity of some Lie algebra. This is some result, but we can derive these equations from the supergeometry analysis. Anyway, we prepare some coordinate, intermediate coordinate. Intermediate means this I indices coordinate. And we can consider these twists. And in this case, U twist give rise to the Schack-Schwarz twist like this. And this is the Schack-Schwarz ansatz. The U function is nothing but the U twist of the supergeometry, right? So we substitute this twist to the equations we obtained. So we obtain and all the equations proposed in the GSS, the compactification. This is the GSS twist by U twist give rise to some the flux terms. This is the internal Guitenberg correction, and this is the internal flux, but we assume this is a constant. So generalized Lie derivative is defined by this derived bracket, so we obtain correct generalized Lie derivative. The closure condition is this equation, so we obtain we substitute proper theta, and we obtain this section condition and the Jacobi identity. Okay, you can obtain this equation by all the equations. Finally, we comment about the totally covariant formulation. We can consider totally covariant formulation of DFT, and in the term of pre-QP manifold. In order to totally covariant formulation, we introduce a kind of connection term. This is a kind generally affine connection term, then the spin connection term. So by introducing connection, we can construct a totally covariant formalism of QP manifold, so we can obtain totally covariant DFT. In fact, Gauzy-Nabla, first bracket of Gauzy-Nabla and vector field give rise to covariant derivative, of generalized covariant derivative of vector field. And if we impose this Fierban postulate, we obtain the relation of connection, order connection, and this is this is the generalization of the normal connection and the Whitehead connection, affine connection, spin connection. And we obtain that this is automatically satisfied. So from this equation we obtain the covariant derivative of the space-time metric is equal to 0. And we can define covariantized Hamiltonian function like this. And we can obtain the covariantized generalized Lie derivative by derived bracket. The closure condition is also covariantized, right? So as I mentioned, this is a covariant version of the section condition. We need a spin connection, the Whitehead connection, and this affine connection for the vector field. Okay. A twist, we can consider twist. We can introduce generalized fluxes, and we can obtain the covariantized version of generalized Bianchi identity by this one. This equation. This equation is because this equation is not is independent of coordinate independent. This application of the covariant version is the DFT on group manifold. We can apply covariant version to covariantized version to the DFT on group manifold. In this case, the generalized derivative on the internal space is nothing but the B bracket of these two generator. So we obtain some, this is a constant. Generalized derivative is this constant, this spin connection is constant. So spin connection, but general Lie derivative relation, we consider if we substitute Lie derivative definition of Lie derivative, this is a structure constant, we obtain the proper relation. This is the relation of the spin connection and the structure constant, like this. This is correct relation of in the DFT on group manifold, and we obtain generalized Lie derivative. Okay, so we can derive all the Bianchi identity of the equations for group manifold, the DFT on group manifold. We can compute. Anyway, I very briefly explained the two applications, GSS compactification and the DFT on group manifold. But we can consider more general setting in DFT by we construct coordinate independent formulation of the DFT equations. Finally, I summarize the result. We have formulated DFT geometry by supergeometry in terms of QP manifold. And generally, the real derivative is defined like this, derived bracket, and we can define closure condition like this. This is weak master equation, and the flux is all the flux is introduced by this twist, and all the generalized Bianchi identity is derived from this one equations. This is the result. So it's time. It's stop. I stop. Thank you very much.
I have two questions. First one, I probably missed some step. When you presented the version which is invariant with respect to different organisms or double space, was that due to the introduction of some background expectation to the mind? How did it happen?
Yeah, I assume the ODD invariant metric. We assume ODD invariant metric, but we don't assume any background metric, background structure. Right. Constant eta or the in the covariantized case we assume GLD structure. So GL2D, we assume GL2D invariant metric in the curved metric. But yeah. Finally, we can we introduce the background, the combination of background Vierbein and some of the background Vierbein and Vierbein and the fluctuation Vierbein. Yeah. Right. Yeah.
My other question is sort of the question about terminology that we understand what you do. When you say master equation, is it just like a half the OST?
This is the
master equation.
Yeah, it is we choose. We consider choose the analogous.
It's Q,
because otherwise you could have some generalization of the framework.
We choose the analogous terminology. Yeah, it is in some sense it is in some sense this equation is equivalent, the same as the classical master equation. We can classical in the BV master equation. We can consider. Yeah, this we can consider topological sigma model using this the Q structure.
No, but I think that
I'm
saying don't use the word BV. I mean, you are doing graded geometry and you all vectors will satisfy.
Right.
Graded has nothing to do with BV. BV is much more special setup.
All right.
So the word BV should be removed.
Well, it is just a thing.
Right, but it's a
terminology is very.
It's a graded symplectic geometry, and you can have different. BV is a very special setup.
Right. Yes.
Exactly. Don't use the word BV when it's not actually necessary. That's why I complain, and that's why Martin is getting confused. I mean, you don't need to use the word BV. I mean, I know it sounds sexy and more attractive.
No, I don't. I really disagree. I think some sexy.
it's also
But that's
But
relation.
symplectic and infinity has nothing to do with degree.
No, that's not
said
true. That's not
it's a structure. It's a symplectic form of degree of one is not also very special.
Yeah, in some, in the, okay. Sure.
Are there any other questions? If not, let's let the speaker again.